Here we go into some more optimization and two more classic problems. And the first one is all about finding the minimum distance between a graph and a point not on the graph. Say what? Well, it says, what point on the graph of g of x equals root x plus 3 is closest to the point 1, 0? Okay, so we're going to draw just like a rough sketch. When I say rough sketch, I mean super rough. Root x plus 3 is something that looks roughly like that. Right? It's root x shifted to the left 3. And then 1, 0 is a point somewhere around here. We want to find the point on this curve, or points, that are closest to this. So how do we do that? Well, if I draw out the picture, let's just assume that the closest point is somewhere like, I don't know, here. And I could be wrong with where it is. Right? But I'm just going to call that point x, comma, y. Right? I just know that on the picture that's the case. So if we're talking about the closest point, we're really talking about the minimum distance. So we want to minimize the distance. Well, the distance, you got to know your distance formula, is the square root of. Now you got 2 points here. So the distance formula is the difference in the x values. So in this case, that'd be x minus 1. And you're squaring that out. Plus, and then it would be the difference in the y values squared. Y minus 0 squared. So again, the distance formula overall, for those of you hankering for it, is x2 minus x1 squared plus y2 minus y1. I'm not going to go over the derivation of this formula, though it is really cool. That's the distance formula. Now, let's keep with this one right here. So let's keep going there. Now, usually we have a secondary equation. And here we kind of actually already have it, because this y value is that value right here. And that y value is always going to be determined by the curve, because this point that we're finding is the point that is on the curve. So y is described as root x plus 3. And so we now have this equation of x minus 1 squared plus g of x is y, or root x plus 3, minus 0 is just root x plus 3 squared. Now, something else very special about this, and this is often shown in textbooks, and some teachers will go over this. If you're finding the minimum, we now need to take a derivative. However, the distance will be at a minimum, either when you minimize this whole equation with the square root, or if you minimize what's inside the square root. Right? Either way, you're getting the minimum distance. So whether you minimize everything with the square root, or minimize just what's inside the square root, we'll get the minimum distance. Why is that? Well, think about it this way. If you were to square both sides, d squared equals everything inside the square root. Let's just call that stuff. Well, if I now minimize stuff, I've minimized d squared, and therefore have minimized d. And if you're like, I don't really get that, at least follow this idea, because it makes life a lot easier. So I'm going to take everything on the inside, and that's what I'm going to take the derivative of. I'll just call it f of x, the inside of it. That's what I need to minimize. Square root of x plus 3 squared is x plus 3. That saves me a lot of time. So I'll take the derivative. That's going to be 2 times x minus 1 plus 1. Ooh. And then we add up everything, combine some like terms, we're going to get 2x. 2 times minus 1 is minus 2 plus 1 is minus 1. And we'll set the derivative equal to 0. Nice. What we end up with is our critical number, x equals 1/2, which ends up actually being the x value that is going to be on the curve that is closest to 1, 0. Sweet. So what do we do in terms of the sign chart? Well, we've got a whole bunch of values, but we know in terms of the curve, we can't go to the left of -3. So if you really want to, you could do that. Limit us at -3, but you don't have to. So we're going to put down 1/2, and it's f prime that I'm evaluating. And that's going to actually tell us about the distance and where it's increasing or decreasing. So a number to the left of 1/2, 0. We plug it into the part of the derivative here. And so that's going to be 2 times -1 when we plug in 0. It's -2 plus 1 is negative. That's good. We wanted a minimum. Greater than 1/2, 45 billion. 2 times 45 billion minus 1 is positive, plus 1 is positive. So the distance will be decreasing everywhere before 1/2 and increasing everywhere thereafter. The distance between 1, 0 and the point on the curve, that is. Therefore, we have an absolute minimum distance at x equals 1/2. So we need the point, right? So All we do then is plug 1/2 into the function to figure out what that point is. So g of 1/2, ooh, that's going to be a nasty number, is the square root of 1/2 plus 3, which is equal to the square root of 7/2. And don't you dare rationalize that at all. So our point is 1/2 comma root 7/2. Dunzo. And that square root, by the way, extends beyond there, all the way down past the 2. All right, let's do another problem here. It's a slightly tougher one, but a good one and a classic one nonetheless. Again, the key on that distance one is that if everything inside the radical is minimized, then the radical's been minimized. Okay, a rectangular page in a children's book will have 60 inches of print. So how do we deal with this? Well, let's start out with what we have there. So we've got a rectangular page, like so. This is another classic problem. And we've got all kinds of print in here, like so. And it's got 60 square inches of print. So I'll just put a 60 inches squared. Okay. The margins at the bottom, right, and top are 1 inch, but the left is 2 inches. Okay, so this would be 2 inches, and then we'll do 1 inch on every other side. It's not the perfect drawing, but it'll do. So this is 2 inches, 1 inch, 1 inch, and 1 inch. Okay, so how do we deal with this one? Where are our variables? From my experience, I think it's easier to, well, obviously first read to see what we're maximizing. It says, what are the dimensions of the page? So the publisher will use the least amount of paper. That would be area. That's how we measure that. So area, let's think about this. I'm going to call this x and this y. X being this length here, y being that length there. And the reason why I do that and I don't call that x and that y is because my secondary equation is going to come from the 60 that's in here. And I'd much rather write that simply as x times y equals 60. That's my secondary equation. This is a very particular strategy for this particular kind of problem, but I've seen it come up enough in my students' work that I think it's necessary to go over. Then my primary equation is to use the least amount of paper, which is this whole thing. So let's take a look at that. If this is x, we're walking. Imagine walking along this line. You'd do 2 plus x plus 1. So that's 2 plus x plus 1, or x plus 3. That's the dimension of this width right here. And then this would be 1 plus y plus 1. And it's not drawn to scale at all. So 1 plus y plus 1, which would be y plus 2. So the area of the paper, which we're trying to minimize, is x plus 3, that times that, or length times width, times y plus 2. And that is going to be the area, again, that we are going to minimize. Okay, now, in terms of which to solve for, it honestly does not matter. So pick a variable. I guess I'll solve for y, because I like having x. So let's do that. So y is going to be equal to 60 over x. It doesn't matter in this case because plugging in for x or y is pretty much the same. You're adding a number to it no matter what. So this is going to be x plus 3 times y is 60 over x. So 60 over x plus 2. Now please, for the love of calculus, do not take the derivative at this point. You're going to want to distribute or FOIL this out and then take a derivative. It'll be a lot nicer. So a of x now is what we have is equal to x times 60 over x. The x's will divide out. Ooh, that's nice. X times 2, that's 2x. 3 times 60 over x. Well, 3 times 60 is 180 over x. We got this? Okay. 3 times 2 is 6. All right. We're almost ready to take a derivative. Let's kind of neaten it up. We've got 2x plus 180 x to the negative 1, preparing it for differentiation, and 60 plus 6 is 66. All of this and no calculus has yet to be done. Now we'll take a derivative and we'll go through old school work. So think, all right, switch on the old school helmet. Derivative of 2x is 2. The derivative of 180x to the minus 1 is minus 180x to the minus 2. And the derivative of 66 is 0. So now technically, just to be very clear, there is a place where the derivative does not exist. That would be where x equals 0. Right? So that is a critical number. However, x can't be 0 because if it is, there's no width to the page. All right? So look into the context of the problem before you go crazy with your numbers. So x can't be 0. It's got to be greater than that. So we're only going to look for the critical numbers where we're equal to 0. I add 180 over x squared. We end up with 180 over x squared equal to 2. And I multiply both sides by x squared. Nice. Divide by 2. Ooh, so x squared is going to be equal to 90. Okay, not the best square root, but we can deal. And so x is equal to, not plus or minus, just positive root 90. And sure enough, if we do a sign chart, starting it at 0, right, because we've got that limit, we've got the square root of 90 to check. If I plug something less than the square root of 90 into the derivative, 1. 2 minus 180 over 1 is negative. So that means that the area is decreasing everywhere from 0 to root 90. And something greater than that, 5 billion. 180 over 5 billion squared is really small. 2 minus small is positive. So that'll be increasing everywhere thereafter. So we will have an absolute minimum at the square root of 90. So a minimum will happen there. We want the dimensions. Now that's not the dimension, that's just x, right? So how do we find it? Well, we plug it in here. So our dimensions would be root 90 plus 3 by, that's one dimension. Now we need the y value. So that's going to be 60 over root 90. A lot of extra math right here. And you can simplify that down if you want. It's going to bother a lot of people, but I'm going to leave it like that. By 60 over root 90 plus 2. And it's plus 2 again because it's y plus 2. And that's all this problem wrote. It's a classic one, a difficult one, but get used to it. It's going to show up on a test. And if it doesn't, shame on that teacher. It's a good problem. Peace.